suspended between two springs, and I can oscillate it vertically, which is your x direction, like that. So x changes with time. The time axis I will introduce by putting on this string. When the spray paint is going to spray, I'm going to pull on that string, and if I can do that at a constant speed, then you get horizontally the time axis, and of course vertically you will get the position of x. So I want you to just see qualitatively what kind of a weird curve x as a function of time is, which then will have to satisfy that differential equation. All right, it's always a messy experiment because paint is dripping, but I will try to get the spray paint going. There we go. Okay, now pull. All right, you give me a hand? Yeah, could you please?
All right, guys, welcome back. That video clip that was preceding this was Walter Lewin showing what the motion is going to look like for simple harmonic motion. And the beginning of next week, you guys will do a lab where you'll look at that for a mass spring system, a pendulum, and a dot on a rotating disc, which can also be thought of as a clock. So we're thinking about the minute hand or the second hand. All of these are going to obey the same type of motion. So this is the beginning of that lab, and they ask you to draw what this graph is going to look like. So what would the motion look like? Up here it says the simplest form of oscillatory motion can be described by a sine function, which we can write in general form as y equals a sine b t plus c plus d. Suppose y is the vertical position of a mass hanging from a spring measured in meters, and t is time measured in seconds. What are the units of a, b, c, and d? Okay, so looking at this, now rewrite this so it is easy for you to see. So we already know that A is going to be the amplitude, and that is going to be measured in meters. So that means that D is going to be our vertical shift. That's also going to be measured in meters. B, we identified as omega, last part, lowercase omega. And this is our angular frequency. And this is going to be measured in radians per second. And so that means that C is going to be our horizontal shift, right? Because this is our vertical shift. It's possible that our graph won't start perfectly on sine, and whatever that shift is, and we would call that horizontal shift would be measured if this is radians per second times t, which is seconds. I'm stuck with radians, and so C must be measured in radians. Okay, so make this smaller. On here, they want us to draw sine and cosine. So I'm going to make sine red, and we know that sine of 0 is 0. So this is what sine is. I'll make cosine green. I know that cosine of 0 is 1. Or in this case, it would be A, right? Because it's going to be our displacement. And we know that the shift between these is pi over 2. Now, I know it's more common for you guys to use sine than cosine, and that's usually what we start with. In physics, we're going to say the blue graph is more likely what you're going to see with simple harmonic motion. It's more likely that something's going to be displaced by A or negative A and then released. And you start timing it when you let it go, right? So it's more likely you're going to pull a pendulum back and start the timer when you're holding it there at the amplitude, or pulling the spring down and start the timer there, or pushing the spring up. It's less likely that you would let the pendulum go and decide you're going to start timing when it goes past the bottom part, right, where it is at an amplitude of 0. That doesn't seem realistic. So we're going to use this. So our formula for our position, and I will call it generically just X, is going to be A cosine omega t, where omega is not our angular velocity, but our angular frequency. And this is going to be 2 pi over t, or 2 pi f. All right, so a couple of examples. A block on a horizontal frictionless plane is attached. Is attached to a spring as shown above. The block oscillates along the x-axis with simple harmonic motion of amplitude A. So it goes from A to negative A, back and forth. Which of the following statements about the block is correct? So for number 7, at x equals 0, its velocity is 0. That's not true. At x equals 0, it has a maximum kinetic energy, right? That's when it's going fastest because it has no spring energy. At x equals 0, its acceleration is a maximum. That's not true because there's no acceleration, because there's no spring force. At x equals a, its displacement is a maximum. That's a winner. 8, which of the following statements about energy is correct? The potential energy of the spring is at a minimum at x equals 0 is true. So that's when it is all kinetic energy. It would have no potential energy. Another one, an ideal massless spring is fixed to the wall at one end as shown above. A block of mass m is attached to the other end of the spring. It oscillates with an amplitude A on a frictionless horizontal surface. So we only have conservative forces. The maximum speed of the block is Vm. The force constant of the spring is. So we have that energy is conserved. Because it's frictionless. And so when it's all the way compressed, it has potential energy that's 1/2 Ka squared. When it is going past the equilibrium position, when x is equal to 0, it is all kinetic energy, which is 1/2 mvm squared. We want to get A by itself. I can get rid of a 1/2. And I have m vm squared over k square rooted. I'm sorry, over a square rooted. Not square rooted. We're solving for k, not for a. So I would just divide. Sorry about that, guys. So I have m vm squared over a squared. Block 1 is attached to a spring and oscillates on a horizontal frictionless surface. When block 1 is at a point of maximum displacement, block 2 is placed on top of it from directly above without interrupting the oscillation, and the two blocks stick together. How do the maximum kinetic energy and period of oscillation with both blocks compare to those with one block alone? So we don't know this yet because we don't know the period formula, but a bigger mass is going to make it a greater period. the energy of a spring when it's all the way compressed or stretched is stored in the spring itself, not in the mass. So it's 1/2 kx squared. M isn't even in the equation. So it would be D. We don't know this formula yet. I'm about to derive it for you. But it's 2 pi square root of M over K. A student is observing an object of unknown mass that's oscillating horizontally at the end of an ideal spring. The student measures the object's period of oscillation with a stopwatch. The student wishes to determine the spring constant of the spring using the measurements of the period of oscillation. Which of the following other pieces of equipment would provide another measured quantity that is sufficiently information to compete the determination of the spring constant? So you would need if we're using the period, we would need to use a balance too because we would need to get the mass. But again, we don't know that equation yet. Using a number of measurements, the student determines the following. The total energy of the object's spring system is most nearly, so we know our spring constant and our amplitude, so we could use that to get our total energy. We also know the maximum speed, so we could use this as well. I think both of those, each of them are 3.8. But that's the total energy. It's not 7.6. While the object is continuously oscillating, the student determines the maximum speed of the object during 2 oscillations. The first speed is 3.5. The second speed is 2.7. Which of the following could account for the decrease in the object's maximum kinetic energy? So that's telling me that we're missing a non-conservative force. There's a non-conservative force somewhere in my system. So it must have lost energy to the surroundings, whether through acoustic energy or heat energy. A block on a level surface attached to one end of a spring, as shown in the figure above. The other end of the spring is attached to a wall. There's friction between the block and the surface. A person displaces the block from its equilibrium position and releases it. Which of the following shows the mechanical energy as a function of time for the system that includes only the block and the system that includes the block and the spring? So as I mentioned earlier, the block only has kinetic energy. The spring holds the potential energy. So the block and the spring energy is there's friction, so we're losing energy. So the block and the spring energy would start at something and then it would curve down. The block itself would only have kinetic energy, so it would go from having no energy to a lot of energy to no energy to more energy, no energy, energy, no energy, energy, tapering down to the opposite. So D would be our best choice. And if we had the potential energy curve, it would be opposite of this and fill in the gaps to make it look like that.